Welcome to Subnetting 101. As many of you know, subnetting has been the single most challenging subject to ascertain for many students. For whatever reason, the concept of visualizing that the subnet mask drives the network architecture seems to escape many students. Moreover, you may be surprised that many instructional videos on the internet get it wrong. You frequently see videos where tables and charts are whipped out that require periodic table type memorization, which is time-consuming and, frankly, setting you up for failure. Unfortunately, this does culminate to some dire consequences, for this confusion seems to translate to certification scores. However, don't let that discourage you, for yes, there are definitely subnetting questions in the exam, but they're not the majority. In fact, many of the questions revolve around troubleshooting steps. This presentation will try to assist you in easing your frustration by giving you readily available techniques that don't require huge memorization. As for advice on taking exams, flag the performance questions first and move on. Don't even read them. Don't waste your time on getting stressed or nervous about them. Go straight for the multiple choice questions. Rifle through them first, allowing you to go back with hyper focus on the remaining questions. You'll feel much better knowing that you've already completed the majority of the questions as you try to address these performance questions. Now, that being said, remember, when answering multiple choice, trust your gut. First of all, what is subnetting? Originally, the idea was to efficiently partition the addresses in a fashion that was commensurate to the need. Hence, IP subnetting is a method for dividing single physical networks into smaller subnetworks, or subnets for short. This is accomplished by manipulating the 32-bit available addresses in the IP4 construct, which can divide into two parts, a network ID and a host ID. The number of bits you assign to either of the network ID or host ID will provide either a greater number of subnetworks or conversely, a greater number of hosts, depending on what's chosen. Back in the day, when the standard IPv4 classful addressing was the only construct, there were only three partitions that really mattered. Each were defined solely on octets dedicated to the network portion of the address. For a Class A, the first octet, 8 bits, was dedicated to the network, where the balance went to the hosts. For a Class B, the first and second octets, 16 bits, were dedicated to the network, while the last two went to the hosts. And finally, for Class C, the first three octets, 24 bits, were dedicated to the network, where only one octet went to the hosts. Now that we have established that in classful addressing, the address space is divided into three major classes, A, B, and C, where D and E, not discussed here, are reserved for multicast and experimental purposes, respectively. So let's continue and review how a computer can distinguish between the classes. This is done by the order of the bits in the first octet. In other words, the order of the bits in the first octet determine the classes of the IP address. For example, Class A, the first bits of the first octet will always be 0. For a Class B, they will be 1 and 0. And for a Class C, the first bits of the first octet will always be 110. By identifying the class of IP address, the computer intuitively knows what bits in the 32-bit address are dedicated to the range of addresses for the network ID, and conversely, the range of addresses for the host ID. This is what determines what is available for an ISP or a network administrator when assigning IP addresses to each device that is connected to the network. It should be noted here, because of these classification bits, the number of available subnets are impacted. For example, for Class A, instead of the full 8 bits for the network, the dedicated 0 reduces it only to 7 bits to describe the network. Hence, the number of networks available is 2 to the power of 7, or 128 networks can be assigned. For Class B, instead of the full 16 bits for the network, the dedicated 10 reduces it only to 14 bits to describe the network. Hence, the number of networks available is 2 to the power of 14, or 16,384 networks that can be assigned. With these hard fast numbers associated with each class, one can see where classful addressing falls short when it comes to avoiding waste. Specifically, it exhausts the availability of IPv4 addresses faster than need be. To illustrate, the problem would commonly occur when an organization requires more than 254 host machines. Why 254 and not 256? Because that is the number available after you subtract the host address and the broadcast addresses already assigned to each subnet. Anyway, anything above 256 minus 2 addresses in the Class C and therefore would no longer fall in the Class C, but rather the Class B license. This means the organization would use a Class B license even though they had far less than the 65,530 host addresses afforded to them by such a class. Therefore, if an organization only required 255 hosts, they would be wasting about 65,280 host addresses by requiring that next level. It was rapidly realized that if continued, classful addressing would greatly decrease the availability of IPv4 addresses unnecessarily. Before we delve into advanced techniques in subnetting, we should review some basics. Many pose the question, why subnet? Well, you may feel compelled to subnet for many reasons. 1, to more efficiently allocate a limited bank of IP addresses. 2, to improve network performance. Subnetting allows you to confine traffic to where it's relevant. Running lots of network devices on the same subnet can gum up the works, especially if there's a lot of broadcast traffic. And 3, to make IP networks more secure and easier to manage. Creating multiple network partitions allows you to fault isolate network breaches or malware outbreaks. What is a subnet mask? A subnet mask defines a chunk of IP address that is dedicated to the host ID, and which portion is dedicated to the subnetwork ID. The trick is accomplished with a subnet mask, another 32-bit number, which works like a filter, with the mask identifying the IP address bits that represent the network portion with ones, and the bits that represent the host portion with zeros. The more host bits you have, the more devices you can set up. Conversely, the more network bits you have, the more subnets you can set up. However, it's going to be either one or the other, for you only have a fixed 32-bit playing field to deal with. The subnet mask is always a string of ones on the left, followed by a string of zeros on the right. Keep in mind, the subnet mask is not the same thing as an IP address. It does not uniquely identify any device or network. It just tells the router which portion of the IP address it should use to figure out the network ID. You can easily spot a subnet mask when it's represented dotted decimal notation. They always start with 255, which, by the way, is the dead giveaway, for 255 is not a valid octet for any class of IP address. Now, some of you may have noticed that there was use of a /19 notation at the end of the IP address, which in turn translated to the subnet mask. This stems from the classless interdomain routing notation, or otherwise known as CIDR notation. Without getting too deep in the subject, just know that CIDR is a shorthand method for representing a range of IP addresses. For example, let's look at the loopback address of 127.0.0.0/24. It can be represented as 127.0.0/24, and in other words, the /24 represents the immutable portion of the bits that represent the network ID. What I mean by immutable is it cannot be changed or manipulated. This allowing the balance of the bits to be used in any combination of zeros and ones. Another example would be the 32.0.0.0/8 address. And using the CIDR shorthand, we can represent that very same address as 3/8. In short, the first 8 bits will be used to indicate the network IP number, and the remaining 24 bits, or 32 minus 8, would be used to determine the host IP numbers. All 24 remaining bits can be either ones or zeros. This is the same as 2 to the power of 24 numbers in range. So you may ask, how does that translate into a subnet mask? Well, /19 represents the number of ones that mask the network portion of the 32-bit address. So /19 means 19 ones, starting from the left to the right. This is the bits that are designated to be immutable, or the network ID that cannot be changed. So the subnet mask identifies what is the network portion and what is available for the host. And what is available for the hosts? Typically, the entire range of 0 all the way up to 255 in each representative octet. One last item I want to make sure that we review is that you remember how to build the binary octet. What I mean by build it is start with 2 to the power of 0 equals 1. We know that because anything to the power of 0 equals 1. So starting with that, putting 2 to the power of 0 on the top row and 1 on the bottom, we increment 1 by doubling it each time we write it down. 1, 2, 4, 8, 16, 32, 64, and 128. And on the top, we just increment the power of 2 by 1. So 2 to the power 0, 2 to the power 1, 2 to the power 2, etc. And there you have a nice usable template to make sure you don't make any math errors. Now, why is this important? Well, when you take your time to actually try to convert a binary number to a decimal, it becomes incredibly useful. All you have to do is take the binary number of in question and look at the ones. That's like turning on a switch on the decimal number below your little table. So whenever they ask you to convert the ones and zeros to a decimal number, you just look at the ones and write down the corresponding number below it, and then add them together. That's your decimal number. Now that we have completed the compulsories of this exercise, let's review the 3 tips to overcome subnetting. Now, these 3 memory aids were invented to allow you to derive any salient information that you would need to solve a subnetting challenge. Note, there are many techniques out there, and by all means, these methods aren't the only way of getting answers. We just find them to be the most efficient way of doing so. This brings us to tip 1. Find the interesting octet. In many exams, when testing your subnetting prowess, they'll give you an IP address and a subnet mask in decimal notation and ask you, hey, give us the broadcast address and the host range of the given address and the subnet number, which in this case, there's referring to the subnet mask written in / form. First, let's find that subnet number. The decimal notation form is given, so we will just simply convert it to binary and then count the number of ones in the subnet mask. That is the subnet number. From there, you need to find the interesting octet of the mask. Well, just look at the decimal notation and look for the octet that isn't 255 or isn't 0. That is the interesting octet. This will be the octet of focus, the octet that you use to derive the number of subnets as well as the number of hosts. This brings us to our second tip, or what I like to call powers of 2 bring networks and hosts in view. Now, this second tip is a doozy. In fact, it's the workhorse that could be the single tip that helps solve all your subnetting challenges. Incidentally, this is conspicuously missing in many of the subnetting tutorials on the internet. It's simple. When looking at a subnet mask's interesting octet in binary representation, 2 to the power of the total number of ones in that octet equal the number of subnets, and 2 to the total number of zeros in that octet equals the number of hosts. I cannot express the importance of this simple statement, for it supplies the key to every answer in the subnetting realm. The key is to find the interesting octet. Remember, that's the number that's in the mask that's not 255 or 0. And then break it down to binary. Then apply the statement. 2 to the total number of ones equals the number of subnets. And 2 to the total number of zeros equals the number of hosts. Why is this thing so valuable? Well, perhaps an example would be best. Suppose they give you the address 172.21.92.251 with a subnet mask of 255, 255, 240, and 0. And they ask you to find the network segment, the subnet number, the broadcast address, and the host range. Well, right away I look at the subnet mask. The octet 240 is the interesting octet because it's not 255 and it's not 0. So I take 240 and turn it into binary. Now I know binary representation is 4 ones and 4 zeros. Why? Because I remember that 4 ones is 240. However, if I didn't remember that, I can always derive it by adding 128 plus 64 plus 32 plus 16. And that equals 240. I use that from the table that we made earlier in the basics. So applying the statement 2 to the number of ones equals the subnets and 2 to the number of zeros equals the hosts, I can calculate that 2 to the 4 number ones equals 16 subnets, and 2 to the total number of zeros, which is 4, is 16 hosts. From there, I can derive that 16 subnets are separated by 16 addresses. In other words, the networks are 0, 16, 32, 48, 64, and 80. Since the address was given of 172.21.92.251, I noticed that the 92 is in the position of the interesting octet in the subnet mask. That's the number I'll focus on. All I have to do is determine which subnet the giving address falls in by finding the closest number to 92 without going over it. And in this case, it's 80. And guess what? Now we have our network subnet number. Simply place the 80 in the interesting octet position in your given address and 0 anything to the right of it. So now I have the network number of 172.21.80.0. Knowing the network number is 172.21.80.0, we can easily derive the broadcast number by just subtracting 1 from the next network number, which is 96. So we subtract 1 from 172.21.96.0, and we get 172.21.95.255. Note, we're only dealing with network numbers in our subtraction equation. Since then, we remove 1 from the network number and come up with 95. For the host field, we always place 255 for broadcast numbers. Now for the host range, remember, it says host, not network range. So we're already accounting for the fact that the network number and the broadcast number are already taken. Thus, to get the range for eligible hosts, we have to add 1 to the network number and subtract 1 from the broadcast number. Adding 1 to the network number is just 172.21.80.1. And for the upper range, we just subtract 1 from the broadcast number, which we already derived. The broadcast number is 172.21.95.255. Subtracting 1 from that is 172.21.95.254. So to recap, we know since the subnet mask was 255, 255, 240, 0, that the subnet number is /20, which is just 16 bits plus the 4 we borrowed from the 240 octet. Next, since /20 borrows 4 bits from the interesting octet, it leaves 4 zeros. We know the number of hosts is calculated with 2 to the power of number of zeros, which is 16. So now I know my network numbers are incremental by 16. That is 0, 16, 32, 48, 64, 80, etc. By taking the given address, 172.21.92.251, and looking for the octet that matches the position in my interesting octet in my subnet mask, I find the octet contains 92. Now, taking that 92 and seeing where it falls within the incremental numbers of the network numbers without going over, 92 falls in the 80 network. Now, placing that address of 80 in where 92 was in my address and zeroing out any of the host octets, I get 172.21.80.0 is my network address. From that, we immediately know that the broadcast number for the network is just the next network number 96 minus 1, which would leave us 172.16.95.255. As for the first available number, this would be the network number plus 1. 172.21.80.0 is the network number, plus 1, which will leave us 172.21.80.1. And as for the last host available, that would be the broadcast number minus 1. The broadcast number being 172.16.95.255 minus 1, which would leave us 172.16.95.254, since we're dealing with host numbers and not network numbers. And finally, we know the subnet will be the network number with the suffix /20. Finally, this brings up to tip 3, what we call the secret. This is the third and final tip that saves you an amazing amount of time. In fact, this trick, which many either don't know about or forgot to share it in their instructional videos, is the shortcut of all shortcuts. And now, since you went through all the calculations, you may have an appreciation for it even more. Some refer to it as the magic number because it not only gives you the number of the host addresses, but, as you know, is also the incremental addresses between the subnets. Theoretically, if it gives you the IP address and the subnet mask, this technique can derive all the answers from this one trick. Think about it. If you know the number of hosts, you can immediately start calling out the network numbers by that increment until you reach 256. You can't go further than that. As a result, you get the number of subnets as well. Subsequently, it provides not only the network numbers for each subnet, but you can easily derive the broadcast numbers as well by just subtracting 1 from the next subnet. You'll find the method very easy to remember and refreshing. The general rule is subtracting the interesting octet from 256 gives you the host number, basically the magic number.